Okay, so what I want to do is finish up the one problem we had on flux yesterday. You have the new homework, which I cleverly call homework 3 because it follows homework 2. This is Gauss's law stuff on it, and then integration problems and some other stuff. Start this one now. Don't start this the night before because you're not going to get even remotely sure. There's binomial expansions. There's a lot of stuff on here. Start this early, okay? And now here's the bet. Okay. The good news about this assignment is the class isn't going to get any harder than this. Okay. The bad news is it's not going to get a whole lot easier than this. It'll kind of fluctuate some, but the course isn't going to get harder than this. But this has an edge to it, and it's just the nature of the beast. Okay. So we looked at a problem like this. This is X, Y, Z. And we had a little rectangular solid we had here. Okay, tell me what the sides are here because I don't remember. 3?
Yep.
4?
Yep.
2?
Yep.
And then we had electric field here, and what was this? 5I hat? Plus X, Y, Z, J hat?
3 X, Y, Z.
3? Plus, and then it was an X, Y squared Z cubed?
4X squared.
Or X, Y squared Z cubed?
Yeah.
Yeah, like this. And the question is, find the flux through this object. Okay, find the flux. Find the total flux through this object. Okay, so we know our flux is this guy here. And what did we say this breaks into? How many integrals?
6.
Because there are
6.
because there's 6 sides. And so we'll put the top in here. I'll put the bottom. And then I'm just going to say plus the other 4 sides. Just make it easier to write. Okay, so let's start actually doing it. And we started doing it last time. So we started with the top. Okay, how did we, and again, when you do these, actually draw it in there. How does the dA vector look on the top? So the dA vector by definition does what? And always outward. Okay, so it's always perpendicular and then outward. So we came over here. Now, normally I've been drawing like a little tiny loop of area like this, somewhat round patch. Here's how I'm going to do the integral. There's another way to draw this. I'm going to draw like a little tiny square. So I drew this little tiny square like this. And what did we say the width of that little square is in that direction?
Yeah.
Dx. Okay. Then in this direction, actually this side is
UI.
dy. Okay. And then this side,
Yeah.
dx. And then this is going to be the dA vector here. So this dA vector, how do I write it? There's going to be my, let me put in this guy here. Tell me how to write the dA vector? You can put your homework through. You tell me how to write that dA vector now. Dx, dy. You may have said that in your last one. That's the, if you say dx, dy, that's great because that's the magnitude, but it's a vector. Dx, dy, vector.
Yeah.
Okay. So this is dx, dy, so this whole thing here is my dA vector. Is that still on the board? And it is. Ooh, okay. Now, what do you know about I dot K? Close. Is what? So I dot k is 0. Remember, when you take the dot product between any two vectors that are perpendicular at 0, because it's always the magnitude of the first vector, magnitude of the second vector times the cosine of the angle between the two, and the cosine of 90 is 0. Now, what about j dot k? Because they are perpendicular. K dot k. It's going to be 1. So this whole thing here just reduces to this part here. We get this integral on the top, 4xyz cubed dx dy. Okay. Now, let's start beating on this. What do we know about the z on the top? There's a reason why I gave you this type of shape here. On that top part here, so we're doing this integral just on the top, right here. What do we know about the z on the top? It is a constant, so what can I do with it? I can pull it out of the integral. I'm going to write this as z cubed. You can put it right there. So integral to the top, 4xyz dx dy here. Okay, this is a constant. Okay, so now what can I do with this integral here? A lot of you probably haven't seen it yet in calculus yet, but you will. I'm gonna, at this point here, I'm just gonna give you integrals where this nice little thing happens. When you're in Calc 3, you're gonna get some integrals where I'm showing you is not gonna work. It's gonna be, have an edge to it. What you can do is I can actually split this into two integrals be multiplied by each other. I can split this integral up into an integral just involving the x, and an integral just involving the y. I can pull out the 4 as well, too. I'll pull out the 4. So here's an integral, this will be x dx. This gets multiplied, they don't get added, they get multiplied by then this integral of y squared, like that. Now, what are the limits on the x integral from over here?
0 to 3.
This is going from 0 to 3. And then what about, that's a sad 3. Then what about on the y? 0 to 4. 0 to 4. Okay. So let's actually crank that out. Recopy this over here. I'll just write it like this. So that's going to equal 4. Now, what is z on the top? 2. So this would be 2 cubed. The integral of x is
X squared over 2.
x squared over 2. This gets evaluated from 0 to 3. And this gets multiplied by the integral of y squared, which is y cubed over 3. With 4 here like this. And so if you multiply everything through here, you get, this is 8, so this would be 32. This would be 3 squared, which is 9 over 2. And this is 4. What is 4 cubed? 16 times 4. Well, I'll just say 4. 4 cubed over 3. Okay. So that right here, that would be the flux through that top side. Okay. Now, without doing any work, what's going to be the flux through the bottom? Okay, what did you say, Riley? I thought you had something else that came in there. Okay. Yep. Why is it 0? That's actually correct.
It's 0.
Yeah, if you're on the bottom here, what would be the only things that would change here? Okay, so how would the dA vector go for the bottom?
Okay.
Yeah, this would be the dA vector for the bottom. So when I wrote this, it would be dx dy times negative k half. So I get a minus sign in front of all. So that's fine, but what do we know about the z? The z on the bottom part, because of the way I took the picture here, the z on this bottom part is 0, so there is no flux through the bottom. So this would actually be 0 since z equals 0. Okay. We're going to do all the sides. Okay, before we do the easiest one is going to be actually let's go figure out why. Now let's do the right and the left side. Let's look at the right side. You tell me exactly how to do the right side when else goes at this. Take a little square, and I'll even put in a different color. Here's my little square like this. Here's my dA vector. How you write that dA vector for the what would be this side here on my little square? Dx. What about this? Dz. So when I go and do this here, I put in my buddy here, E here. You tell me what to write then for this dA vector. The XEZ,
Yeah.
J hat. You tell me what that is. You take this dA vector and dot it into all these here. What are you left with? What is J dot I? Because perpendicular. Okay. What is J dot J? 1. What is J dot K? 0 because of perpendicular. So this whole thing here, it reduces to this 4x, not bad at all. 3xyz dx dz. Now what can I pull out of that integral and why?
One
Both the y and then the 3. Why can I pull out the y?
constant.
It's a constant, right? I'm doing the integral on this side here, on the right side, right? On the right side, that y is equal to 4. So I can pull that outside here. So this gives me the 3y integral here of an x z dx dz. So what I can do is, again, that integral is going to factor all nice and all nice and smooth. Again, when you get this in Calc 3, they're going to give you funny shapes where that ain't going to happen. So I get this x dx. That gets multiplied then by this integral of z dz. And we need integrals on those, limits on those integrals. What's the limit on my x integral? 0 to 3. And then z? 0 to 2. So what does this give me? This gives me 3. My value y is 4. This gives me x squared over 2, evaluated from 0 to 3. Then this guy here gives me then z squared over 2, evaluated from, oh, that's a, yeah, that is a 2. Good. So this gives me 12 times, put a 3 in there, I get 9 over 2. Put a 2 in there, I get 4 over 2. So this would give me, well, this would be 4, 3, 12, 9 times times 12. What would that be? That would be 808. Okay. What would be the value then on the left side? How come? Yeah, so if I look at my left side, here'd be my DAO here. This would be my DA vector. So if I wanted to write that DA vector, it would be minus dx dz I hat. But again, since I'm on this left side here, the y for this is 0. What I can do is that I can just kind of cheat. I can say then that this right here to the left. And equals 0. Okay. The reason it's going to equal 0 is because that y0, since y equals 0. Okay. Make sense? Now, turns out that the easiest one is going to be the x direction, the flux through the front and the back. Like, just look at that E and tell me why that's going to be the easiest one to do. Tell me about 5I hat. How does 5I hat differ from the y and the z components? Meaning the x component is a constant. Okay, so I can be a lot sloppier with this one. So now let's do the front and the back. I have this right here for the front. I'm going to have my E. I'm going to dot this into, so if I do my front, it's a little, I'll put another color in here. So this right here is that's coming out like this. This is my DA vector for the front. How do I write that DA vector for the front? What is this? DZ. What is this? dy. So my DA vector for the front is going to be dy dz I hat. Okay. So if I take dy dz I hat and dot it into E, what is that going to leave me here? Just the 5. So this is going to give me then this integral here on the front. Just 5 dA. Now I could put in here if I wanted to, I could just as well say that this is dy dz. That's fine. I'm just going to cheat because it's a constant, so I know I can get away with it. Why can I cheat? If you want, you could put, I could say the dA is dy dz and do all the integrals and everything's fine. Okay. Then let's cheat. And the 5 comes out of the integral. What is an integration process? When you integrate, what are you doing? Summing up tiny little things. If I take a little dA here, that's my little dA, and sum them up over the whole front, what does that have to give me? The area of the front. Okay. This has to just equal A, which is the area of the front. Well, what is the area of that front? Three times. Well, 3?
No, 4 times 2.
4 times 2. Okay. It's 4 times 2. This is the area. That's an 8, so this is going to be 40. That make sense? Now, if you wanted to, again, you could put in that this is dy dz. You can go through and put in all the limits, just like we did over here, and you get the same thing, but it takes longer to do, so why do it? Now, what about the back? Hmm? Hmm? It can't be 0. Why did we have the left? bottom here. Why were they 0? Because if you look at the left term here, there's a y in it. If you look at the bottom term here, it has a z in it. On the bottom, the z is 0, and on the left, the y is 0. Okay, so they're 0. Well, what happens with the x direction? It's a constant. Okay, so that you're not going to get the 0 coming in there. Okay, but I'm lazy. So what can I do?
Same as.
Almost. I almost like your answer. Okay, so this picture is getting cluttered. I'll draw this little picture over here. So here's my backside like that. So if I look at a backside like that, my dA vector, how does the dA vector go for the backside? It goes like that. So that dA vector is going to be what? It's going to be this minus dy dz. There's a minus sign here. So what are you going to get here? You get the exact same thing, but with a minus sign here. That makes sense? What happens here when you do the actual backside? I'll put this on the back. And this is going to equal minus this 5 times dA. This is on the back. And this can be within this minus 40. So if you want the total flux here, you have to add together all those terms, right? You're going to add together basically the front plus the back. And what would most rooms do? They're going to cancel. Okay. Then you're going to have to add to that the top, the bottom. Okay, and this one here was 0. Then you're going to have to add to that the right plus the left. And this one here is 0. And this is equal to some value I'm just going to call star. Now, suppose I want to know the total charge enclosed in that box. What would be, so for part B here, find Q enclosed. What would then be the charge enclosed in that box? Why? I don't know. Hey, why might I ask you to calculate the total flux for all the sides, and then ask you Q enclosed? What is this connected with? It's the electric flux, which is connected to the Maxwell's equations, Gauss's law. This is equal to give me the name of it, epsilon naught, okay, which is a permittivity of free space. That's what you have. Look at this. Okay, we know that this is Q enclosed over epsilon naught. For Q enclosed, it's just our epsilon naught. That's our flux. We found our flux at star, so this is just going to be epsilon naught times star. Okay. Hey, let's look at this crazy new homework you have. That says start early. Okay, let's turn the page. We're looking at the third page. Looks like we have a cube with an E field going through it. And number 5. If we look at number 4, it looks like we have another cube with an E field going through it. Okay. Wonder what you're going to do with those. Now, let's actually start using Gauss's law for what you can use it for. So Gauss's law The law is always true, but it's going to be a really easy way to calculate the electric field for three simple geometries. So, Gauss's law is often used to calculate the E field for three simple geometries. And I want to go over what those geometries are. There's going to be something you're going to think is simple, and then I'm going to try to convince you not today, but later on, that it's not simple at all. It's pathological. Okay. So what do you think simple geometries might be? There's usually one that's mentioned that turns out to be pathological. So what would be three simple geometries? That's the one that always gets mentioned because it's basically how difficult could a cube be? Okay, there's some things I haven't taught you yet, but we're going to come back and look at the cube. It turns out the cube is absolutely pathological. That is an absolutely pathological object to look at, a cube, which sounds so stupid because it's a cube. Okay, no, if you see, that's why people are scared of the Borg in Star Trek. They're a cube. Everyone realizes that cubes are complicated. Now I understand Star Trek. Cubes are going to be pathological, okay, for a very profound reason. Okay.
You're looking for 2D or 3D?
It's all 3D.
There.
Sphere, something with spherical symmetry. So spherical geometry. Okay, the next two are not that's the only obvious one. Next two are not one bit obvious, okay? Because of two words we have to put in front. Okay, so it'd be another simple geometry. If you have a sphere, you might have a cylinder now, and there's going to be a cylinder, but here's the trick. It has to be an infinite cylinder. Okay, so you're going to see an infinite cylinder. So infinite cylindrical geometry. And the next one is not one bit obvious. It's going to be the infinite plane. So what I want to do is we're going to take each of these and just start cranking them out. Let's start with spherical because you're most used to it. Actually, no, maybe not. Yeah, we'll do spherical. And then I'll do a cylindrical one. Then you're going to start tinkering with them and stuff like this. And this is going to seem very odd when you first start them. Once this clicks, this is going to be very easy. But it takes a little while for this to click. And just so you know, this is going to be on the first test. And it turns out we still need it on the second test. So you might think, well, okay, after the first test, I'm glad I'm done with Gauss's law. No, you're not. Okay, it just comes back and it brings its buddies in the second test. Okay. So let's ask, how do you use, so let's use Gauss's law. Find the E field for a point charge. You could say, well, wait, we already know the electric field for a point charge is K2 over R squared, and that's right. I want to show you how I can get it still with this way here. I'll illustrate the points. So, in order to use Gauss's law, follow these steps. If you make this systematic, it turns out to be actually not too bad. Here's the first one. Draw a Gaussian surface with the same symmetry. has a problem. Okay, so we're gonna put this over, I'll put this over here, and then we'll list the rules over here. So here's my charge here, Q. I want to come out some distance here, R, and I want to find E here. Okay, so what's the symmetry of this problem? If it's a point charge. It has spherical symmetry. So what do I want to do? I want to draw a Gaussian surface with that exact same symmetry. And since I want to find the electric field here, I'm going to start my Gaussian surface here, but keep that cylindrical symmetry, spherical symmetry by drawing a Gaussian surface like this. I draw a big sphere like this. That's a sphere. This is a spherical Gaussian surface. Okay. Next part. Label E and dA on all sides. Okay, right now you can say, well, there's, it's like this. There's really not all sides on this. Just put down all sides. You'll see when you do the cylindrical case why we see that. Okay, so I picked my favorite spot here. Where's my favorite spot to draw the electric field? Doesn't matter, right? Spherical symmetry. So I picked some spot on I want to find my electric field on the surface here. So I'm going to draw it someplace here. I'm going to pick here for no good reason. So this is my E. At this spot here, right? So this is E. This is my R. At this spot here, how does the dA vector go? Again, the dA vector by definition always does what? Normal and outward. So I draw my little dA vector here. That's my dA vector. Okay. 3, calculate this guy here. Let's calculate it for this case. Okay, how do you do a dot product? Magnitude of E, magnitude times cosine of the angle between the two vectors. This magnitude of E, magnitude of dA, cosine of what angle does that E make with dA? 0. What is the cosine of 0? Now here's one of the subtle spots here. Where are we doing this integral? What are we integrating on? On the Gaussian surface. By symmetry, right? This integral is being done on the Gaussian surface. By symmetry, what do you know about the magnitude of E anywhere on that Gaussian surface? By symmetry. It's a constant. It's a constant. What can I do with that electric field then? And you're all pros at this. When you're integrating, you have a constant. What can you do with the constant? You can pull it out of the integral. Okay, so here's the key here. But this right here, magnitude of E is a constant. It's not that the magnitude of E is a constant. It isn't. It varies all over the place. But on the Gaussian surface, which is where the integral is being done, it is a constant. So is a constant on, and that's the operative word, on the Gaussian surface. So I can pull this outside of here. Now, so if I take a little patch of area dA here and sum them up over the whole sphere, what do you have to end up with then? The area of the surface of a sphere. So this ends up equaling E times the area of a sphere, surface area of a sphere. Okay, engineers and physicists and mathematicians. What is the area of a sphere, a radius r? Time delay. That tightening is just my heart kind of just being clenched and it's being just squeezed.
I heard you.
Oh, wow. That's like this, sorry. Okay, well, tell me why it can't be r cubed. Anything with an r cubed would not be an area, it would be a volume. There is a pi r squared. So this is going to be a. There is a pi and there is an r squared. Ah,
One
wow. 4, right? 4 pi r squared is the surface area of a sphere. Okay, next step is then just calculate then your Q enclosed. In this case here, what is the charge enclosed in the Gaussian surface? And it's as stupid as you think it's going to be. Get your picture. What's it just a charge enclosed? Q, done. Okay. In this case here is Q. And then use Gauss's law. So now we know that this is a case. And my buddy here is this magnitude of E, 4 pi r squared. This is my friend Q. Am I just calling it capital Q? I'm calling it capital Q here. Sorry, I changed my notation on you. So I take over the 4 pi and I get magnitude of V equals 1 over 4 pi epsilon naught Q over r squared. What did we have before? We say it's electric field of a point charge. KQ over r squared. Hey, if I compare these two here, what do we have? K is 1 over 4 pi epsilon naught. So this gives us here that it's K. It's 1 over 4 pi. That's 1 naught. Now, if you remember before, I told you I wasn't going to tell you what epsilon naught is, because I told you there's going to be a dumb way to calculate it. Okay, K is easy to know what it is, because what is K?
9 times.
9 times 10 to the 9th, an easy one to remember. So this is easy to remember. So our epsilon naught, just 1 over 4 pi. Hey, should have 1 over 4 pi times 10 to the 9, 10 to the 9th. I mean, times 9 times 10 to the 9th. And then you can just calculate it. And then you know the units for K, and then this is just going to have to flip those units. Okay. Let's try one that's a little more involved now. Let's try doing the infinite wire. We're going to come back and look at more of these here. What we're going to do is we're going to start looking at a sphere, and then we're going to have a charge density in the sphere. We're going to start looking at a lot of really crazy things. Okay. Let's do another example. What is the for a uniformly charged infinite wire. So here's my infinite wire. Obviously, it's not infinite, but I've already drawn this. Imagine it has positive charge on here. This is the uniform charge. I'm going to come out some distance here, R. I want to find E here. Okay. Now, we have two ways of finding the electric fields. What are they? What was the first way we had for finding the electric field of an object? Treating the object as a bunch of point charges and then doing what? Integrating over the whole thing. Okay, that's one way. The other way now we have is Gauss's law, but how can you tell if you're going to use it to do a Gauss's law problem? Gauss's law is always true, but you can only easily use it for those three simple geometries. Okay, so what you look here, you'd see that basically you have this infinite wire that's uniformly charged. You'd immediately think Gauss's law. Okay. Hey, let's look at a little homework here. Okay, let's look at let's look at number 9 here. Okay, it looks like somebody gave us an infinite wire with with the outer radius B, and somebody put a hole in it of some radius A, but it's an infinite wire here. When you calculate the electric field here, what method are you going to use? Because it's one of our three geometries that's going to be a Gauss's law problem. Okay. So whenever you hear the words like you have a sphere or anything like an infinite wire, you think Gauss's law. So what are the rules for Gauss's law? What's the first thing we do? Or the first rule? Get all the Gaussian surface with the same symmetry as the problem. So what kind of symmetry do you have? It has to be a closed surface. So what kind of symmetry do you have for a infinite cylinder or an infinite wire? Can't be infinite because it always has to be a finite thing, but it'd be some sort of like cylinder. So what I'm going to do is I'm going to draw a little cylinder here like this. I'm going to come down here. This is going to have some length here, L. Like this, it has to be a finite surface like this, like that. So here's my Gaussian surface. Now, what's the next part you do on that Gaussian surface? You what? Okay, label what? The E field and the dA vector on all surfaces. Okay, so let's do the dA vector first. This is why we have to deal with all surfaces. How many surfaces do we have here? We have 3. What are they? Top, bottom, and someplace on the side. So if I live on the top here, how does my dA vector go? It goes up. So here's my dA vector, like that. I can put this dA vector anywhere on the top, it doesn't matter. How about if I live on the bottom? Down. Because again, the dA vector by definition always does what? Yeah, it's always perpendicular normal to the surface and it always goes outward. Now I pick my favorite spot on the side. It doesn't matter where I do it. I'm either going to draw over here, just make it easier to draw. I draw it over here. It'll be like this. This is my dA. So I do my little thing here. Do this right here. I put dA here on the top, flux on the top, and I have flux on the bottom. And flux on the sides. Okay, now we have to do one thing here. This we have to think a little bit about. We have to now figure out what the electric field looks like for this. So if I had an infinite wire like this, how would the electric field look? This one we haven't looked at, we're gonna have to think about it.
Going up.
Okay, so if it's here, it is coming out, so let's say if it's, here's my wire. So let's say I'm here. How do you think the electric field is gonna look here for an infinite wire? I want to convince you that it goes out like this. No matter where you are, this is electric field is gonna go out. So what I want to convince you of is that if, has everyone had chemistry and cleaned out a test tube? Okay, what do you do with the, you have your little test tube, you have that little metal brush and you go like this, and it seems like all you do in chemistry is clean glassware. That's all I did. So you clean glassware with that little metal brush. Okay, so that little metal brush, the metal bristles that come out like this, that's what the electric field is going to look like for an infinite wire. In other words, if here's my wire like that, imagine the electric field's coming out like this in all directions. So it's kind of from a top view. If here's the wire coming out like this, that electric field is going to come out like this. If you have the side view, then basically what you would have is, you can't really draw it though. It looks like the metal bristles coming out of a test tube coin. Does that make sense? Convince me of that now. Let's say here's a wire like this. We do the convincing, then we'll finish this up on Friday. Let's say here's my infinite wire. Let's say I want to find the electric field here. What was one way we said we could always find the electric field? I could treat the wire as a whole bunch of point charges. So I'm going to put a little line here like this. So if I look at a little point charge here, dq, how does the electric field look here due to my little friend dq? Yeah, this would have to be this one here. Now let's show this some distance here, x. Now if I come over here, distance here, x. So it's the one that corresponds to here. How's the electric field look at this spot due to my little friend here, dq? It goes like this. Hey, what's going to happen? Yeah, if I break this into components like this, these cancel here, and I'm just going to be left with an electric field that goes this way like that. I could do that anywhere along here, so that electric field always comes out like this. Okay. So think about what that means about this kind of. We'll finish. We'll call the class here. We'll wind up. Think about what that's going to mean for this case over here. Okay. Have a good day. So everyone have the homework. Okay. And again, this homework, that little warning here is, not minor. Okay. This has an edge to it. Oh, Zali, I got your email and I've been running around. It's all yesterday.